Hello everyone and welcome to the next webinar series. I am Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are excited to delve into today's webinar titled Overview of Soil Stabilization Using Synthetic Organic Polymers. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes. You may use the question box to ask questions during the webinar, and our speaker will be happy to address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificates will be available in ACI University under the Certificates tab within 2 days. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning unit. Please take note of our disclaimer on the screen for the next webinar series. So let's get started with a short description of our today's webinar. This webinar aims to provide insights into the historical background, recent research, and advancement related to the use of synthetic polymers for soil stabilization in engineering applications. It will delve into the benefits, challenges, and potentials of the innovative soil treatment techniques in the civil engineering projects. Our learning objectives for this webinar are as shown on the screen. So let's welcome and introduce our today's speaker, Dr. Pupala and Dr. Jason Wang. So I'll give a brief introduction. So Dr. Anand Pupala is the Chair of Civil and Environmental Engineering at Texas A&M University, and he serves as a Director of the Center of Infrastructure Renewal, CIR. He is a distinguished researcher in geotechnical engineering with a focus on sustainable soil stabilization. He has remarkable publication and has secured research grants exceeding 30 million from federal, state, and local government agencies. So let's welcome him. And our co-speaker is Dr. Jason Wang. He is currently working as a postdoctoral researcher at Texas A&M University. He received his doctorate degree in civil engineering from the same university. Dr. Wang's research interest includes soil stabilization, polymer stabilization, material characterization, soil mineralogy, pavement geotechnics, and infrastructure resilience. Let's welcome both our speaker, and I will hand it over to them.
Thank you, Aparna. I think I'll wait as just again, one more thing. I'm a chair professor, not a chair of the department, but that's okay because it gets confusing. The chair professor in the Department of Civil Engineering at TAMU. Thank you again.
Thank you for the correction. Thank you.
No, that's okay. Thank you. I just want to mention before I start the presentation, the ACI Next for funding this project. I want to mention Dr. Gusaya Elaitan, Dr. Aparna Deshmukh, and G. Jimates. And they all supported our project. We have completed. We're about to finish our final report. I also want to thank my friend, Dr. Tony Nanny, for introducing me to the ACI Next group. This is very helpful for all of us. So thank you. They're a really great group to work with. Thank you, guys. So with that, let me start with our presentation outline. So we'll be mostly Jason is going to be giving the entire depth of the material, and I'll be beginning with a couple of slides, and then also will come at the end to close it. So our outline here is basically we start with the introduction of the stabilization a little bit, then we'll go into polymeric materials. There's so many polymeric materials, so it can be it can take some time to get into these details. I think if you work in this area, I think this will help you definitely with time. Then we also talk about our research is predominantly literature overview and collecting it, including some case study that Jason's PhD work is on this topic. Polymeric stabilization is going to discuss. And also we did some survey where we collected some of the industry practitioners, to get some of the details on polymeric stabilization. I'll talk about some of the challenges and opportunities, and then we'll end with a summary and discussion. So I think, many of you already mentioned that you are working on stabilization for various products. So the way you define soil stabilization is majority of the soils that we have in the ground are weak in certain way or some problematic conditions. We're talking about soft soils, expansive soils, collapsible soils. So when we have to design our infrastructure, particularly like transportation or a residential infrastructure, the first thing we have to do is we have to improve their performance. So that means you have to stabilize them so that they're more stronger and also less volume, less swelling and shrinking type materials. So that's where we use different products for stabilization. And our stabilization is again can be done in different ways. You can use physically, or mechanically, or use chemically. There are many ways. So the one we are focusing today is actually going to be talking about polymeric, which is considered as a chemical stabilization process. Many of you are familiar with traditional stabilizations in the practice. Most of these stabilization products include cement, lime, and different types of fly ashes, and also slags in grounded form, and also asphalt emulsion. That's also very frequently used product for stabilization. And then the ones that we are now we see are more and more practice is non-traditional stabilizers. So one of the materials are polymer. I see a lot of polymeric stabilization papers these days at the ASC and different conferences on the polymeric treatments. There's a lot out there. Most of them are predominantly lab work, but you also hear sometimes bacteria, MICP, or enzyme, or different types. So our particular focus for this today's webinar is on polymeric treatment. So what exactly a polymer? All these, what types of products are out there, how they can stabilize, what are the, how do they work? This information will be shared by Jason. So I will ask Jason to start his presentation from this slide onwards. Jason, so over to you.
Okay, thank you, Dr. Papala, for the introduction to soil stabilizations. As he mentioned earlier, what is a polymer? And for civil engineers, it's always a mystery. So for us, I would just use simple terms to explain what are the polymers and their properties. So we will understand how they perform in the field or in soil stabilization. So first, the polymers, they are organic macromolecules formed by polymerization from repeating units. We call those monomers. So the monomers can be as simple as an atom or a rather complex molecule. I have a structure here, and as an example, you can see this is a simple polymer. After polymerization, the carbon-carbon double bond break, and then linked with other same molecules form a polymer. So in polymers, we call this polymer by their names, poly something. So that something is usually the monomer, so that we know what polymer they are. And for these polymers, they have a functional group. In this case, it's the COOH. These functional groups usually determines the property of the polymer, eventually determine their performance. So before we start talking about different polymer products, there are a few terms that I would like to explain briefly so that we won't get confused later on when we talk about a lot more polymers. I already covered the monomers and polymers. So another term we normally see is the copolymer. What is that? Use the same example here. In this polymer, you can see the number of monomer is only one. So the repeating units are the same. We call those polymers homopolymers. So now, similarly, copolymer means there are two monomers. They alternating, eventually linked to form a large chain material. So those are copolymers. And another term that we often heard are the emulsions. And what are those? To talk about that, I would like to explain briefly about the solutions first. When a polymer is water soluble, we mix it with water, eventually turn it into a solution. That's pretty straightforward. However, for emulsions, it's not as simple as that. Some polymers, they don't dissolve in water. So if you just mix it, it won't evenly distribute in the water medium. So in that case, other chemicals need to be added, and those chemicals can add as a bridge between those polymers and the water, and then eventually they form a uniformly distributed emulsion. Actually, a lot of polymer products, they name it some emulsion. That's why you may heard of this word a lot. And both emulsion and solutions, they are liquid polymers. And for a lot of other polymers, they have solid forms. It's good to know what forms we have so that we know how we will apply them. later on in our research or in the field practice. And also the polymers can be naturally occurred or they are synthetic products. Most of the polymers that we talk about here today are synthetic polymers. And here are a few examples of the common types of polymers that people have been using for soil stabilization. I highlighted their functional groups, and also by their names, you will see what their monomers are. For example, polyvinyl acetate. That just means the monomer is vinyl acetate. So basically, after learning what polymers are, we will know the chemical compositions of those polymers, which will help us to select those polymers. And I'll talk a little bit about these polymers because most of them are widely used in the current research and the studies. So the acrylic polymer, this is one of the most common polymers used to produce polymer emulsions for soil stabilization. And they are usually the derivatives of acrylic acid or methacrylic acid. Here are the pictures. And because of their functional groups, they are quite versatile. So most of polymer manufacturers use these polymers to form an emulsion, like what we're showing here. And another common type of polymer that people use to produce emulsions are the polyvinyl acetate or polyvinyl alcohol. And here are the structure of these. And for polyvinyl acetate, you may don't know what is polyvinyl acetate, but you may heard of it as a wood glue or some other type of glues. This is because of these polymers, they have the adhesive properties. And another common type of polymers are polyacrylamide. These polymers are a family of polymers of a wide range of molecular weights, and they are quite water soluble. They could form a gel and usually are sold in solution or solid forms. However, there's one thing I would like to point out are the polymers, or shortly PAM. Technically, they're neutrally charged. However, if you go through all the polymer products, especially PAM product, people may say we have anionic PAM or cationic PAM. This is because this polymer, even if they call it PAM, they are actually a copolymer of acrylamide with other monomers. And if you remember what structure they are actually the acrylic acid and their derivatives. So these are the polymers that have been used to produce different copolymers. And then the next one is the polyurethane. You may heard of this name as a lot of in forms of foams or an insulation material. Yes, that's correct. However, for soil stabilization, we don't use those foams directly. And more specifically, some researchers, they use the one component polyurethane, which is actually the isocyanate. And these components react with the hydroxyl groups within a polymer or simply water to form a product which will bind the soils and other things. And this polyurethane is often used to produce the resins, the pens, and foams. You might be familiar with this. And all the polymers that we talked about earlier are all in liquid forms. However, in soil stabilization, we also use the solid type of polymers for stabilization. For example, the polypropylene or polyethylene, and these are in fibers. So we have covered a few of them, or the most common one. This slide shows a overview or a summary of the current types of polymers that have been used in soil stabilization. We can see besides the 5 or 6 types that we covered, there are many more polymers, such as the polystyresulfonate or the butane, tetracarboxylic acid, all those. However, what we just covered, if you compare them carefully here, if you look at them carefully, we'll see we already covered probably 70% of the polymers that have been used. And what type of soil have been used in polymer stabilization? This is a result based on, I think, over 200 studies. And we can see that the majority of the researchers use choose sandy and clay soil for study. And we also find that the polymers may be suitable for some problematic soils, such as the sulfate-rich soils, the high salinity soils, frozen soils, organic clays. And you may be wondering, okay, how do they perform their research? If I'm new to this, how do they test it? How do we apply it in the field? This is a flowchart that we developed as we work with the ACI Next to develop, trying to develop a guideline for polymer stabilization. So in this flowchart, you can see, if you are already familiar with soil stabilization with the regular stabilizers, most of these things are quite similar. And basically you can consider, I personally consider as like two parts. One is the sample preparation, or including the material selection, the prepare polymer solutions, determine the polymer dosage or polymer content, and then prepare the samples. And then the the second part is the examination of their engineering properties. And we'll cover a little bit in detail about some of the key aspects in this research so that you'll have a better idea. And for polymers, instead of using polymer alone as a primary stabilizer, there are more research now showing possibility of using the polymers as a secondary stabilizer in conjunction with, for example, cement. And in that case, the procedure are pretty much similar. We just need to kind of change it a little bit, because the primary stabilizer now is the traditional stabilizer. So we may change our curing method or mixing criteria, something like that. So now let's talk a little bit more about the polymer selection. How do we select the polymer? As we covered earlier, we have different types of polymers, acrylic acid, among others. And it is always important for us to know those types of polymers, what functional groups are available, what charges they have, and what are the options for, for example, different molecular weights, different viscosity, and their solubility. Will they solve in water or will they not? And also, are they only in liquid form or in solid form? Because once we have those in mind, it will help us to select the product that we want and eliminate a lot of other things that we don't want. However, even in this step, sometimes it's challenging because there's no established universal criteria for such a selection because of the wide variety of these polymers. And also, sometimes we say, okay, we covered 6 groups basically earlier. Even within that 6 groups, there could be thousands of different variations. Each one of them can have quite distinct chemical properties. So that's why it's quite difficult to just select that polymer based on the material itself. So what we recommend here is based on their performance. So basically, we select a polymer based on our own knowledge and experience, and we do some laboratory studies to investigate the property that we care. For example, the unconfined compressive strength. And then many other tests depends on the application. For example, for pavements, we're probably gonna measure the resilient modulus. And for the other slope stability, we may measure the shear strength and the cohesion and all those parameters. So this is the criteria that we suggest. And of course, a field study is always something that's very important. And then about the mix design, we'll talk about the polymer content, their compaction, and then the mixing and the sample preparation, as well as the curing. All those may sound already familiar if you already know the stabilization of soil with the traditional stabilizers. However, there are a few things that are quite different because the polymer in nature, they're quite different from cement or lime. For example, the polymer content. If we just find a paper or if we compare 5 or 10 papers, sometimes we find it confusing about the polymer content that people have been using. Some people say that they use 0.1%. Some people say we use 20%, 30%. In that case, it's always confusing to me at the beginning of my research. I'm like, wait, then how can I compare these products? How do I know if that one is good or better than the other or not? And what after our studies and a lot of analysis on the research literature paper, and we find like there's one thing that a lot of people are missing here, that is the effective polymer content, which is defined as the ratio of the solid polymer to the dry soil. Because some people, they just use the solution, whatever is in there, water, polymer, and other things, they consider that weight and to define their polymer content, which causes them to, because a lot of water in there, they will say they actually use 20% of their stabilizer. However, that solution itself may have only 50% of solid in there. So the actual effective polymer content in that case will only be 10%. So by doing this, we're able to compare between different products, and which really help us a lot to understand and to understand different polymers and their performance and compare with other polymers or even other traditional stabilizers like cement in terms of the polymer content that they use and the strength that they bring. And for the compaction, as you may know, for soils, the density probably determines the property, or can the strength of the soil can be highly affected by the compaction. If the quality is not good, it could skew the data. So that's why for the compaction test, we just follow the standards to determine the optimal moisture content and the maximum dry density, and to compact our samples at that state. And for mixing, this is some people talk about, well, how do we mix things? Because sometimes polymer itself contains water in there if it's a solution, and also that water may not be enough to reach OMC, so it causes the mixing sequence difference. And actually, later on, I'm going to show some results to see that there is some effect based on how you mix all these ingredients. And the same thing for the sample preparation and then the curing. We always need to know those conditions eventually can help us evaluate how they perform. And when it comes to the mechanical tests, even if there are no standards for polymer stabilized soils, but we have a lot for the general stabilized soil, so like all these test lists here, we can still follow this and to measure the properties that we want for a project and then evaluate the performance of the polymers. And another aspect for the polymer stabilization are their durability. And one of them is the moisture sensitivity. Here, we want to know how polymers will perform when moisture gets involved. For example, the one on the top left are one of our group's research, a PhD research work to try to investigate the vinyl acid ethylene is a copolymer and treated with the soil. And then in other researchers, you find research that you can see that people just soak the sample completely underwater to see the difference. And some others use the capillary soaking. And another important thing to evaluate, or we need to pay attention, are the degradation of polymers, because polymers, they're organics. Sometimes they will degrade based on due to thermal changes, mechanical changes, or even biological or chemical reactions. So here I just covered earlier I covered some of the details. Now let's look at the whole picture of so far what people have been doing with the polymer stabilization. And here I list the types of polymers that people have been used, and also the types of soils, they're the property that people measure, and as well also the durability. We can see here most of the research still focuses on the unconfined compressive strength. There are some other tests on the shrinkage swell and the shear. However, compared to the unconfined compressive strength, we can see that we definitely need more researches in there so that we can fully understand how these polymers would perform. And when it comes to durability compared to other geotechnical property tests, we'll see that it's pretty lacking at the moment. And we really, however, at this point, we really want to know how durable these materials are if we mix the polymer with soil, how long they're going to last, or under different weathering conditions or freeze-thaw cycles or wet-dry conditions, how durable they will be. And also another trend that you can see at the bottom half of the table are people trying to use different polymers with cement. And however, because it's relatively new or even newer than the polymers, we actually don't have as many research results compared to the polymers. And here are some of the results that I summarized from all those. From here, you can see the findings. I highlighted those in green, which means the polymer shows the promising effects once mixed with the soil, and such as the swelling potential reduced or the improved strength, both the unconfined compressive strength and the shear strength, and cohesion increase. And also in the red fonts, you will see the some report that their polymers or polymer treated soils are susceptible to moisture and freezing. So those are the things that I summarize all those so that we can evaluate each type of polymer better. And another thing that I would like to point out about the polymer dosage here, you can see here 5%, 10%, 15% for this product by this researcher. And then for the similar product, people use it only like 0.5% and 2%. And this is because of the definition or inconsistent definition of the polymer dosage or polymer content that I talked about earlier. Because of that, sometimes by just looking at the numbers, it's really difficult to have an idea. Is this polymer actually working or not? Do we really need to add that many polymer products into the soil? And here are a few more tables about different the 5 or 6 types of polymers that we covered earlier. And you can see for PAM, they even use 0.002%. And I believe this one, it's the effective polymer content. So that's why it'll be beneficial for us if we just convert all these to the effective polymer content, then we can compare different polymer products. And similarly, we can find the conclusions about the effects of these polymers as the other polymer product. And here are 2 more slides about the polypropylene fibers and the polyethylene fibers. So after the talking about all the overview of the result in the literature, I'm going to show you with 2 slides about my own research. This was my PhD work. I used 2 types of polymers. One is positively charged, one is negatively charged to stabilize a sandy soil. And we can see here, for the reason why I choose these polymers are because I know the properties, a lot of properties about these polymers. I know their availability, the molecular weight, their water solubility, and their charges, and all those things. So what my research, my PhD study results show that we can see a few common parameters: the effect of the dosage of the polymer solution, or the concentration of the solution itself, as well as the molecular weight. So we can find that overall, when you add more polymer product to the soil, the strength will improve. And on the bottom right, this graph shows if I convert all the polymer content to the effective polymer content, we will see a clear trend of how the strength will develop with the polymers. And also we can see that we actually didn't add much polymer product to the soil. The same conclusion is shown for the other polymer, the negatively charged polymer, the PSS. So we can see the effect of the molecular weight. If you in general, if the polymer has a higher molecular weight, that means that they're longer. They can bind with the soil better than the shorter ones. So we'll see the effect of the polymer molecular weight as well. And then for this one, the effect of different molecular weight. And then on the bottom half, I compare my samples to cure for 7 days and 28 days. This is because of the lack of standards. We really don't know how long we need to cure our polymer treated soils. So I follow the traditional way, 7 days and 28 days at those for cement treated soil. We can see that basically there's no difference for this type of polymer between 7 and 28 days. And we can say that, okay, polymer, probably we don't need to curate for that long. It'll gain strength relatively rapid. And then for the last one, it shows the mixing sequence 1 and 2. Here, the mixing 1 means I mix the polymer with the soil first, the concentrated polymer solution with the soil first. And then there will be some water needed for reaching the OMC. Then those mixture, or that amount of water or extra amount of water is added last. And then for mixing sequence 2, the polymers are dissolved in water first. Because they're water soluble, I can make it diluted because of the addition of extra water, and then just mix the diluted polymer with the soil. And you can see that we will see some difference. And for me personally, I prefer the mixing sequence 2 because polymer, they mix really well with the water, and then we can dilute them. It'll become easier to apply to the field or mix with the soil. However, for concentrated polymers, especially with a high molecular weight, they can be really viscous and sometimes it's difficult to mix it uniformly with the soil. So these results just showed us the effect of how the polymer molecular weight, their concentrations, their different forms, the curing time, and the mixing has on their performance. And for this one, this slide is about the field application. Currently, when we did our research about all the studies in polymer stabilization, most of those we found are from the laboratory studies. And the data from well-documented systematic field application for polymer soil stabilization is actually lacking. We find some cases, however, they mix either some information was hidden. We don't know what exactly they are. We don't know what their mix design is, how they mixed it with the soil in the field, or we mix some of the data during the performance. So which makes it really difficult for us to judge a polymer, how would it work? And so that's why for currently we really think that we need more field applications of different polymer products, so that we can fully understand if this polymer would work or not. And when it comes to the field applications, there are a few aspects that are really important to basically kind of quality control when it comes to the field applications of polymers in soil stabilization. One is the moisture content, because a lot of polymers, they may be soluble in water or partially soluble in water. That could bring issues. And also the moisture itself, when it comes to construction, because we're dealing with the soil, when there's too much moisture, we won't be able to compact the soil to their densest state. We call them the density that we wanted, which could cause, if that happens, we'll probably compromise the effect of we might compromise their mechanical performance. And then another thing that's unique to polymer are their viscosity, because for cement, we don't need to think about it. It's a dry powder we mix with the soil. However, for polymers in field application, usually they're sprayed directly with on top of the soil and then mixed. However, polymers, like I mentioned earlier, they could have different molecular weights. Once the molecular weight are high enough, they could be very viscous. And so we need to think about those and choose the correct molecular weight as well as the concentration of the polymer for the easy application. And then the other factors include the uniform mixing, so that we know the quality of the field work is good enough. And then the determination of the polymer content that we need to add to the soil. And then of course the compaction if it's required for the project. And then lastly, the curing. So these are the aspects that we need to consider when it comes to field application of polymers. And now I'm going to give it to Dr. Pupala so that he will wrap our presentation up with the challenges and opportunities as well as the summaries of our presentation. Dr. Pupala.
Thank you, Jason. Thank you. I think as Jason showed a summary of various slides, It's a challenging field, polymeric stabilization, because of so many different types of polymers and how they are mixed. And when we did the survey before our presentation, I see that challenges were mentioned. Lack of knowledge is one of them. And then also being a new material, sometimes you have a more scrutiny. And this is like, I think, a majority of you, second highest ranked in that poll. So that shows that a lot of challenges out there. So one of the things we did as a part of our project is we did a survey, a nationwide survey. In fact, I should say an international survey. We wanted to see how many, what are their challenges that they face when they're using polymeric salt stabilization. So these are some of the things that are mentioned. I'm not going to go over every one of them, but there are some of them that you also did in the survey. Lack of standards, maybe insufficient durability studies. If you look at the table that Jason showed, a small amount of durability studies are only focused, which is typical, because when we do the mixed design, you look for certain property improvement, but we have to make sure that property improvement is permanent. So for that, you have to do durability type of process, which includes either wetting, drying, or freezing, thawing. There are very few studies on that particular one. And then other things is like the stabilization dosages, which I think clearly mentioned. That sometimes, from one study to another study, different numbers, but actually the way they define in their studies are slightly different. So that's why it may confuse sometimes. How come he is using 10%, whereas the other person is using 1%? But the way they define is different dosages. So these things sometimes, as we researchers or practitioners would love to see some uniformity. That is one of the things mentioned in this challenges. They like to see how to do that. Also, they want to see the systematic study, which includes almost all the way, cradle to grave kind of process, where you want to see not only initial understanding of the stabilizer dose, and then also dosages, mixed design, then do some durability, and then go into some test sections. This is something is an important part. So the challenges always gives or leads to opportunities. So we feel there are many opportunities in this area, and as see the benefits sometimes are very important here. Polymeric treatments can be faster, and then can improve in certain types of soils. So that's and also mixing is very quick in the field. Like I think Jason clearly mentioned, the different solution or emulsion ways, you can really spread it. You can do it also on the slope configuration, depending on what type of infrastructure you're dealing. You can do it very nicely with the spraying and then also mixing, and that's something is also offered, provides an opportunity. So that's one thing we'll say. We definitely need a universal testing and reliable mix design, but we have to understand that there's so many polymers. So we're not going to be only one flow chart or one methodology. So it kind of specific to different types of polymeric families. Then also, as I mentioned, durability studies is something we are focusing. We do need, I think this is something that I'm very happy to hear, that anytime you have a new material, there's always a challenge, but that challenge can be overcome by placing some test sections in the field. Majority of our projects with the transportation sector, we always have the last part of our project includes some test sections in the field and monitor them for a certain time. We actually do for various products, including stabilizers, geosynthetics, and all types. So I think this is one area where I think would like to see some champions to come up and say, hey, would love to try some test sections in the field. It can be a small test section, doesn't have to be too long, to 200 to 300 feet of a road section with a polymeric treatment, and to see how it performs in real field. Because sometimes from real field, we see that we learn quite a few things. Lab is not always can be mimicked very well in the field. So there's always challenges, but that's where, if you mix both lab and field study, you can come up with a more improved a protocol of this using these materials. We do think this provides very good alternative stabilizer in practice, because I mean, at certain times it could be maybe coadditive. So I can see why there are a lot more paper research going on polymeric treatment, because of the way they're mixing and the quick application, rapid treatments, and also some good mechanisms of property improvements. There is also room for this type of products in the market. So I'm not going to spend most of this thing, but one thing I want to highlight here in this slide is Jason did a very nice overview of all the things what we have in the polymeric treatments. And one thing I also mention is the last two steps. If you look at it, systematic studies and also field investigations, This is something I've been discussing with ACI Next group, with Gusai and Aparna and and Jerji about this particular need, and also some life cycle cost analysis. For that, you need some performance data. We can do a nice life cycle cost analysis of these products, how they do. Again, maybe focus on a couple of polymers, and then with some field test section, one can see if is the treatment is durable, or there may be some issues. So these kind of things is something I feel like will add more value to this type of product. And then naturally, as the research is progressing with all these systematic studies, we could lead to a more like a design guidance documents, and also some nice documents that can be used for hopefully working with ACI next, so that we could come up with this type of products. For these to develop them, you really need a good systematic study. So that is one of the major needs. So at this point, concludes our presentation. I would like to hand over to Aparna to say, we would be happy to answer any questions you may have. Thank you. Over to you,
Yeah.
Aparna.
Thank you so much for your outstanding presentation, and for also graciously sharing all your expertise in this field. Yeah, we will go forward with our question answers. We have quite a few questions, like we have decent number of questions. So our first question is, how much will it cost using polymers comparing with other methods?
Jason, go ahead. I think they are not they're definitely expensive depending on product, but there's so many different polymers. So this is something I mentioned in the last bullet point. Like, we were thinking about cost part of the analysis. Cost can be a little bit high, but again, as the product shows big market, cost can come down. Certain polymers, maybe based on where they are coming from, where the polymeric industry is based, you could get a locally much. I would not say it's cheaper polymeric product, but definitely moderate expensive. But that means the traditional stabilizers are not cheap either, so they're comparable in my opinion. But that's something I think I would like to. Me and Jason always talk about this thing. There's always they're not really we want to say these are expensive, but I think our goal is cost definitely should be a part of your adaptation in the field, and that's something. But I think these products, in our opinion, quick application, rapid mixing, and also moderate to high cost will allow them to be a good candidates to be considered in the field. So I'm not going to give a one quick answer. Hey, this is only this many dollars. No, it varies because you can see so many products. So Jason, you want to add anything on what you did in your study and the cost wise?
Well, you already summarized it pretty good. I just want to point out one more thing. The cost, it really depends on how we calculate our cost. We can just look at the material cost itself, or we consider the whole life cycle, like how much strength it gives me, how many polymer products. Like I mentioned earlier, we only use, for some of them, 0.5% of effective polymer content. Then even if they may be expensive, but then we only add a small amount of polymer in there. And then if their mechanical performance are as similar to the cement, well, with for example, 10% cement or 9% cement, then the cost is really, we have to do all the calculation, consider all the economics, like their benefits and disadvantages and everything, and then including even for cement, I heard that there are like tax on the carbon footprint or something like that. So I guess if we consider those, then the cost, we may be surprised like which one is cheaper or not.
Okay. Yeah, great. Thank you. Our next question is, with regards to the environment, are there any environmental considerations or concerns associated with the use of synthetic organic polymers in soil stabilization? So I think, environmental effect is.
Yeah, and I think that's a really good question, because we are facing a lot of comments like that when we do our research, when we have our presentations, because it's a big thing. How safe are those things, those synthetic polymers? And I would say it really depends on the polymer product. Some of the polymers, they are actually safe to use. For example, PAM, they have been used for water treatment. So it goes into the water body, and some other polymers as well, they are actually like safe. However, it really depends on what that term safe, how do you determine safe? Because some other people from chemical part, they may think well, nothing other than water or use the food are safe. So I think we also need to consider that. But yeah, it's definitely one thing to address. And also when we select our polymer products at the beginning, we also need to keep that in mind. And we will try to avoid those that are hazardous to our environment or living things. Yeah.
I think, yeah, I just agree with Jason. Definitely, the products that we are using, we have the chemical sheets, so we can check and see if they are. So everything what we do is actually we are already used in different types of sectors. So that's what we are using. So it should be okay, but also at the same time, some things what we do is some of these stabilizations in the field, even with some new materials, we always do some leachate studies. That way, in the field, leachates are different from what you do in the lab. So you will see that leachate, whether you quantify them in some parts per million, whatever, and see if they're environmentally, they're going to cause any contamination issues or any types of soil or water pollution. We can actually look at them. So, but I think, in my opinion, the product, like as Jason said, the products we are using are mostly are used already in different sectors, so they're definitely usable in geotechnical or soil stabilization applications.
As we talk about environmental too, our next question is a little bit similar, but it's on carbon footprint. So it says like, do you have a carbon or GHG load efficiency compared to the OPC, say axis in your comparison? Are there any trends in polymer carbon loads?
That's a really an excellent question. I actually want to mention one thing is polymers are not, I mean, the manufacturing process are not always carbon friendly. The polymers can be a very time consuming carbon friendly, like it not necessarily gives a very high good carbon footprint. So that said, again, as I said, uh, the amount used, depending on that, I think Jason was mentioning before also, you have to look at dosages and then maybe as a co-additive, look and see what kind of carbon footprint. In my opinion, together, like, maybe as a primary or secondary, there could be a way where we can really quantify the carbon footprint of this stabilization. And then depending on that, what is the carbon footprint that of individual polymer, we can see if that makes sense in comparing with a OPC or other types of products. So that is something is happening with the green stabilization method that being out there. But again, a lot of these new products, when we do initially, I just want to alert everyone, it may not show you exact carbon footprint like a very friendly, okay, but that doesn't mean that we should stop them, because there is always room for these methods down the line. Like I think one thing we me and Jason always talk about is the life cycle cost analysis. If you are comparing, let's say this product is providing a more resilient foundation system, less maintenance, less repairs, all those things have to be included in that whole analysis of the footprint. That will show you that maybe a lot less traffic jams, or maybe you're not closing one particular section of a road. Those things have to be incorporated into the whole thing. And also the repair should be fast and rapid, particularly if you are working in an urban environment. So these things are all like, one should look into it. So for us, it's initial, like just looking at the polymeric carbon footprint, is we know that it's not a highly, like, compared to like other products, it's not a very carbon friendly material in that sense, but it is certain types we can actually bring it down. And that is some area. In fact, I was talking to Jason, sustainability analysis of these products is something of a very important. I hope more researchers, practitioners will jump onto that area. So down the line, you'll see same thing. It happened with other products like geosynthetics. There was always an issue with the carbon footprint. But I think, when they show you the high resiliency benefits, sometimes this carbon sustainability carbon footprint may take, I'm not going to say that they may take lower seat, but may balance out a little bit. So I know this is a little bit long explanation, but again, I can't just say, you don't want to say black and white. This is always a gray area. One needs to work on it, so before you can see a good understanding of the full sustainability assessments. Jason,
Yeah.
feel free to add any.
No, I have nothing to add. Perfectly answered.
That's a great answer with honest opinion. That's good. So our next question is, UCS increased with higher concentration. So should concentrations greater than 0.8 be studied?
Jason, I leave it.
Are you talking about this result somewhere here, like 0.8%?
Yeah, Yeah, I think so because it said about UCS increased with higher concentration.
Okay, with higher concentration. Yeah, I think this is something we, I think, yeah, this graph would help to understand, uh, to help answer that question. The reason why we eventually convert the polymer content to the effective polymer content is that we'll kind of have a like threshold of how much polymer we need. In this case, I would say probably 0.6%. It's probably okay. Of course, it depends on our target, how much strength we want to achieve. And for example, if we want it to be 6,000 kPa, then probably we need 0.8. But if we only want it to be like 3,000, it works for us, then that's 0.6. Another thing is if we look at this, this dashed line are the untreated soil. Even at 0.2, it already showed great strength improvement. So when we use those strengths, we're also trying to identify the polymer content that we want to use.
The other thing I may add also, Jason, is like this is what you're seeing is UCS is a mixed design strength. Depending on the type of infrastructure, there may be a targeted strength where you're looking for. That may be enough for the doses. You're right, increasing in doses may increase more strength, but you may not need that kind of high strength for a given infrastructure. Like a lot of infrastructures, they'll tell you how much the subgrade strength, stabilized subgrade strength should be. So that's what our focus is going to be. And then second thing is this is only UCS of a stabilized soil,
Yes.
but we also want to see what happens if I subject this sample to a different wetting drying. Am I going to get what kind of strength am I going to get? Am I going to get retain the strength? So that should be also accounted for. So in a way, you combine with the UCS original strength plus some durability based retained strength together, you will come up with what is the perfect good dosage for real application in the field.
Yeah, great. So moving forward with our next question, we have two more questions we can take. Have any of the polymers you tested have similar results to the straight Portland cement?
I think our study did not compare with the traditional stabilizers, so it's only I think I know Jason worked completely on his study. But in another study we did with the Army Corps of Engineers, we were comparing as a co-additive and different types of additives. There is a that's again, as I said, depending on the certain types of dosage, they are comparable. They're not. I'm not going to say, but depends on what we are looking at the UCS targeted UCS. There is a comparable numbers you can come up with. So, but like again, uh, I I can also see in some areas the cement is more effective than polymers in bringing the strength up. Cement is rapidly increases the soil strength, so sometimes you have to be like you have to see what exactly you're looking for. So I'm not going to say everything. Oh, you should use polymer. There are some areas where maybe cement makes more sense than the polymer. So there is always room for every product, in my opinion. And as I said, as we look at it, maybe there's a balanced design is what I think nowadays asphalt industry does, balanced mixed design. So in this case also maybe a balanced approach is important for stabilized soils also to attain certain strength. So yeah, I think they're comparable, but again, as I said, um, not every soil has seen a good increase in strength of polymer treatment. So
Great, thank you. And the last question is, what consideration should engineers and construction professionals should take into account when choosing synthetic organic polymers for soil stabilization?
yes, and I can take it and then you can complete it. Okay. I think it's a great question also. Like it's excellent questions. Thank you for all these great questions. One thing is like as I said, we did it as a literature review. So one thing we showed in our last but slide is some challenge opportunities. So to me, that opportunities is where like a systematic study is very important. So if I had to do a mixed design, if I had to choose a design, depending on the project type, I'll give you an example. Let's say I'm doing a dam embankment, and the embankment is like maybe a erosion, and I found a certain type of polymer can be a good product, and I can do a spraying very quickly because this is at a at an angle. So I just use some kind of a pump at the base of the toe of the dam, and then apply this treatment, and then mix it, and then rapidly I can finish the project. So depending on the type of project or infrastructure, and also how quickly I had to do the work. Nowadays, time is money. So a lot of times rapid repairs, rapid construction is where, whether it's a DoD, a Department of Defense, or other types of DOT projects, this is where I think there's a role for this material. So if a quick treatment, quick and durable treatment, and then it will also meet the property requirements, there is a room for this material. But I think the one thing that we obviously have the limitation is how durable these are. Are there any field studies to show that they're working well? Very few studies on that part, on that particular part. I think once you start seeing it, I think that people will start coming around. So at the beginning, you will see some reluctance because, I mean, not reluctance, should say, it's more like people want to know what the environmental issues, degradations. There are a lot of the questions that came up earlier. These are very rightful questions, and again, these questions can be addressable, and with the research also we can do it. And as I said, not everything will work, and also we should not also rule out all the things. Also, we should be able to do with a more like an approach that includes all understanding of everything, and then come up with a best approach, best stabilizer that works for field. So, Jason, you could also add anything to that discussion.
Well, thank you, Dr. Papala, for the great answer to that question. I think there's one thing I want to add is it's always good for us to understand the product that we're going to use. For example, the polymers, there are already a lot of challenges facing us. We have to answer a lot of questions because it's a new product. So I think it may look overwhelming at this time because all those problems you haven't addressed those. But eventually we need to learn our product, understand them, like what polymers can do that the other stabilizers cannot, or maybe not as good as polymers. And then what polymers are lacking or they won't contribute that much. And then once we understand those, and based on the knowledge that we have about other stabilizers, then we can select which product that we're going to use. Is the polymer is good for this scenario, and then the cement is better for the other. So yeah, that's what I want to add.
No, I think that's really great. Thank you for answering all the questions, and thank you for the audience for asking these interesting questions. So this ends our question and answer session. So this is the slide for our upcoming webinars. And please do visit aciuniversity.com to register. And with this, we complete this webinar, and thank you all for joining today's webinar, and we look forward to have you again with us in our next webinar. Thank you so much.